Did the universe have a beginning? If it did have a beginning, how did it happen?
Why is the universe as bizarre as it seems to be?
Will the universe have an end? Will it have a death?
Why is the universe so apparently complex? Why is it so rich? Why isn't it simpler?
Cosmologists are coming up with some of those answers today.
We've learned more about the universe in the last few decades than in the rest of human civilization put together.
One thing we do know today is that our universe is getting bigger.
If we look at our universe today, we find that it's expanding. The galaxies that are a long way away from our galaxy are moving away from us.
This discovery was made in the 1920s by the astronomer Edwin Hubble with the biggest telescope of his day.
He pointed that telescope at distant galaxies. For the first time, we could see those distant galaxies. And he noticed something very funny about the light from them. The light from those galaxies was redshifted. That meant those galaxies were moving away from us. If you stand at the side of the road and you hear an ambulance drive past, you'll hear the siren on the ambulance as a high-pitched sound, and then the ambulance will drive past and the pitch of the siren will go low. The reason the pitch of the sound is changing is not because the siren's note is changing, it's because the ambulance is moving relative to us. There's a similar process for light, only this time it doesn't affect the noise, because light doesn't make a noise, it affects the colour of the light.
Like sound, light travels out from its source as a wave. Different colours of light have different wavelengths. Blue light has a relatively short wavelength, while red light has a relatively long wavelength. If an object is moving away from you, then the wavelength of the light is stretched. It moves towards the red end of the spectrum, and so we call this redshift. Every galaxy Hubble looked at was rushing away from ours.
He realised that the further away the galaxy was, the bigger the redshift of the light. That meant those galaxies were moving away from us at faster and faster speeds. It's not that the galaxies are moving apart, it's the fact that the entire universe is expanding. The whole of space is getting bigger.
Turned on its head, and this discovery leads us to an astonishing conclusion.
If something's bigger today than it was yesterday, then yesterday it was smaller than it is today.
Just trying to run the movie backwards, you have to conclude, it's not rocket science, that all the matter that we see today must at one time have been in a very dense and hot region of space. And that is the phase that we call the Big Bang.
We've now more direct evidence that our universe started with the Big Bang.
If we can look in the right way at the universe, we should be able to see the afterglow from the Big Bang, the heat left over from the Big Bang.
Astronomers were looking for the smoke left after the fireworks, and sure enough, when they looked, they found it. This is a picture of the heat left over from the Big Bang. It is a picture of our early universe, and like a fossil record, it also gives us clues to how our universe evolved.
This early universe is spotty. It's like a spotty baby. It has hot and cold spots. These hot and cold spots are absolutely fundamental. It tells us that when the universe was the human equivalent of 1 day old, it wasn't perfectly uniform. It already had in it the seeds of the galaxies and the other structures that we see in the universe today.
So it turns out to make a universe like the one we see today, all we need is gas, hydrogen gas, and gravity. Now, gravity comes for free in our universe, and it turns out to make stars and galaxies is very easy. You simply take that gas that was formed in the Big Bang and you wait.
As we've seen, the early universe wasn't perfectly uniform. It had hot and cold spots. After about 380,000 years, the super-hot early universe had cooled enough for atoms of hydrogen to form, and this gas gathered in the cool spots. As matter gathers, it produces gravity. More gravity attracts more matter, and so on, until you end up with the stars and the galaxies we see today.
We've all looked up at the stars at night and wondered about them. But can you imagine what it would feel like if you looked up at the stars and you saw nothing, no stars at all? Well, that's what it was like for about 200 million years after the Big Bang. As the universe expanded, it got colder and colder and darker, and frankly less and less like a place that might produce things like you and me. Astronomers call this part of the universe's history the Dark Ages. During the Dark Ages, you had a lot of atoms flowing through space. You had about 75% of them were hydrogen with 1 proton, about 25%, most of the rest, were helium with 2 protons, and there was a tiny sprinkling of beryllium, of lithium. Lithium's got 3, beryllium's got 4 protons, and finally of boron. There was also stuff that astronomers call dark matter, quite frankly, because they don't understand what it is. But it doesn't seem to play much of a role in the story, so we're going to ignore it. The whole universe was really very, very simple. We know this because of studies of the cosmic background radiation that was released, you'll remember, about 380,000 years after the Big Bang. What that shows is that matter was distributed extremely evenly through the universe. Everywhere you looked, you seemed to have the same temperature, the same density, the same types of atoms. Really, everything was uniform, and that's a real problem, because it seems as if the universe was just too simple, too uniform for anything interesting to happen. How could you produce you and me from such a universe? Well, we actually know how this happened, and the key players in all of this are stars. So what we're going to do in this unit is we're going to focus on how the first stars appeared. We'll see throughout this course that more complex things seem to appear when you have just the right Goldilocks conditions for their appearance. Not too hot, not too cold, not too big, not too small, not too close together, not too far apart. You get the idea. So what were the perfect Goldilocks conditions for creating just a bit more complexity in the early universe? Well, it turns out that those conditions were scattered all through the universe. The crucial things you needed were, first, lots of matter, secondly, gravity, and third, tiny differences in the distribution of that matter. And they were all there. Recent studies of the cosmic background radiation using special satellites, such as the WMAP satellite, have shown that in fact there were tiny differences in the temperature of the cosmic background radiation. Some regions, for example, were just 1,000th of a degree hotter than other regions. Now this was just enough for gravity to get to work. And what gravity could do was to magnify those differences and turn them into something much more interesting. And so this is what happened. Gravity began to get to work on those differences, and eventually it created stars, something entirely new. So let's see how this works. Gravity, you'll remember, is one of the 4 fundamental forces, and it's the star of this part of the story. As Newton showed, gravity is more powerful where there's more stuff and when things are closer together. Now, to give an example, the gravitational pull of the Earth is extremely powerful on you, but if you move away out into space, it suddenly gets much, much weaker. So now let's move back to the early universe and think how this force might have worked. Remember, there are some areas that are just slightly hotter and slightly denser than others. In those areas, gravity was just slightly more powerful. So what it did was it clumped those areas together. As they clumped together, they got denser, so the power of gravity increased, and they began to clump even further together. Gravity increases, so the whole thing is clumping a bit like a runaway train, and this gets faster and faster and faster. And now what happens is at the center of each of those clouds of atoms, atoms begin to bang into each other really violently, and they begin to heat up, particularly at the center, where there are the most atoms. Now notice something. So far, our story has been about a universe that's cooling down. Suddenly, we're talking about an area of the universe that's beginning to heat up for the first time. Eventually, the temperature reaches about 3,000 degrees. Now, that temperature should sound familiar. It's the temperature at which atoms can't hold together anymore because protons can't hold on to electrons. So what happens is you recreate the sort of plasma that existed before the creation of the cosmic background radiation. Now, the temperature in the cloud keeps rising until eventually it reaches 10 million degrees. And something spectacular happens at that temperature. Protons start banging together so violently that they overcome the repulsion of their positive charges and they fuse together and are now held together by the strong nuclear force. As that happens, there's a huge release of energy as some of their matter is turned into pure energy. This is very similar to what happens in an H-bomb. So now, at the center of the cloud, we have a sort of furnace that's pushing back against the force of gravity and that stabilizes the whole thing. And now what's happened is a star has lit up. And that star is going to shine for millions or billions of years. We've now crossed our second major threshold of complexity in this course. From about 200 million years after the Big Bang, the universe starts filling up with stars, billions and billions and billions of them. And the universe is now a much more interesting place. Instead of the sort of uniform mush that we saw before the appearance of the first stars, we now have a universe that's filled with stars. It's not just that it's more interesting to look at. Stars are much more important than that. Our universe is filled with these sort of glowing batteries that emanate light and heat. It's a much more interesting place. In fact, astronomers can see stars still forming today. It's a process that's still going on. They find them in star nurseries. They're some of the most beautiful places you can see in the heavens. And in fact, it's worth going onto the Hubble website or looking through a telescope at some of these star nurseries, because they're amongst the most beautiful sights you can see in the sky. Stars increase the complexity of the universe in another way. They gave it new types of structure at many different scales, from the level of the stars themselves, to galaxies, to superclusters. So let me try and describe these structures one by one. Let's begin with the stars. Stars themselves have a very clear structure. At the center, you've got protons that are at an extremely high temperature, as we've seen, and they're fusing to form helium nuclei. Just around the center, around the core, you have a sort of store of protons ready to be fused eventually when they sink down into the center. Now, photons of energy and light from the center slowly work their way through the plasma, taking sometimes thousands of years, until eventually they reach the surface and then they flash out into space. So stars have a lot of structure, but stars themselves are gathered together by gravity into much larger structure. We call these galaxies. Our Milky Way is our galaxy. It contains perhaps 100 billion, some say 200 billion stars. It's absolutely huge. And there may be 100 billion galaxies in the entire universe. But structures exist at even larger scales too. Gravity gathers galaxies together into what are called clusters. Our local group is a cluster like that. It contains about 30 galaxies, including Andromeda and the Magellanic Clouds, both of which you can see with the naked eye. Gravity can even hold clusters together to form what are called superclusters. These scatter through the universe in huge webs and sort of chains. But beyond that, gravity is too weak to hold superclusters together. And it's beyond the level of superclusters that you begin to see finally what Hubble saw. You see whole superclusters moving apart, and there, at that scale, you can see the expansion of the universe. Now we've got stars, and stars are going to be the key to later forms of complexity. Most of the universe was then, and still is, cold, dark, empty, and from our perspective, very, very boring indeed. But with stars, you have something like campfires in Antarctica, lights that light up a cold universe. And we'll see that from now on, the Goldilocks conditions for further complexity are to be found not throughout the whole universe, but in galaxies, and above all, around the stars, those cold campfires. That's where our story is going to go now.
But there is another more mysterious ingredient. When we study galaxies closely, it appears that they are spinning too fast to hold themselves together. There doesn't appear to be enough gravity to stop the stars from flying off into space.
Physics tells us there must be some gravity produced by matter that you just don't see. That's what today we call dark matter.
And for the universe to behave as it does, there must be about 5 times more of this invisible dark matter than there is of visible matter.
The dark matter is the circus master. It calls the tune. The dark matter is the force that has sculpted our universe. Without dark matter, there would be no galaxies. Without galaxies, there would be no stars. Without stars, there would be no planets. Without planets, there would be no people. We owe our existence to dark matter. Simple as that. No dark matter, no people.
It's taken around 13 billion years for our visible universe to get to where it is today. But what does the future hold? Until about 10 years ago, cosmologists had 3 theories for what would happen to our universe. 1, that the amount of gravity in the universe would slow its expansion down until it collapsed back in on itself. 2, if there wasn't enough gravity, then the universe would keep slowly expanding forever. And 3, that there would be just the perfect amount of gravity so that the universe grew to a particular size and then stopped. But then astronomers discovered something completely unexpected.
Astronomers have made this amazing discovery. The expansion of the universe is accelerating. Now, how can that be? Astronomers realize there must be something pushing. We don't know what it is, but we know it's there. And this agency that is causing this accelerated expansion, it's called the dark energy.
So it appears that although we've answered a lot of the big questions, we are still left with many more.
We don't know what is the dark matter. We know it's there. We don't know what it is.
What went bang? What happened in the very early stages of our universe? We don't know the answer to that either.
We haven't got the faintest clue as to what our universe is going to be doing billions of years from now. We just don't know because we don't understand the dark energy.
We need help, you know. If there are any scientists out there, young people who want to try and answer these questions, we need help because we don't understand an awful lot about the universe.
There's a lot to play for and lots of exciting new discoveries waiting to be made.
It's expanding. The galaxies that are a long way away from our galaxy are moving away from us.
This discovery was made in the 1920s by the astronomer Edwin Hubble, with the biggest telescope of his day.
He pointed that telescope at distant galaxies. For the first time, we could see those distant galaxies, and he noticed something very funny about the light from them. The light from those galaxies was redshifted. That meant that light doesn't make a noise, it affects the colour of the light.
Like sound, light travels out from its source as a wave. Different colours of light have different wavelengths. Blue light has a relatively short wavelength, while red light has a relatively long wavelength. If an object is moving away from you, then the wavelength of the light is stretched. It moves towards the...
Will the universe have an end? Will it have a death?
Why is the universe so apparently complex? Why is it so rich? Why isn't it simpler?
Cosmologists are coming up with some of those answers today.
We've learned more about the universe in the last few decades than in the rest of human civilization put together.
One thing we do know today is that our universe is getting bigger.
If we look at our universe today, we find that those galaxies were moving away from us. If you stand at the side of the road and you hear an ambulance drive past, you'll hear the siren on the ambulance as a high-pitched sound, and then the ambulance will drive past and the pitch of the siren will go low. The reason the pitch of the sound is changing is not because the siren's note is changing, it's because the ambulance is moving relative to us. There's a similar process for light, only this time it doesn't affect the noise, because did the universe have a beginning? If it did have a beginning, how did it happen?
Why is the universe as bizarre as it seems to be?